So my last video was pretty popular. When I polled what to do for the next one, I honestly wasn't expecting this option to win out, but it looks like it did, and I'm delighted about that. Not only do I think it's good to follow a video about a negative incident with something positive, but I suspect a lot of people are wondering exactly how does one go about even beginning to design a safe deep submergence vehicle. I'm going to start by clarifying I won't be referencing the previous video in this, nor will I be doing a side-by-side comparison, as I think that would be an insult to all the crew who've worked on Alvin. So with that out of the way, let's find out how to build your DSV properly. The meticulous design, verification and operating of Alvin. Alvin is a science and research deep submergence vehicle. It's owned by the US Navy, but operated by a civilian organisation, the Woods Hole Oceanographic Institution. It was the first vessel of its type, with its first iteration being launched in 1964. However, it's very important to note that Alvin is a true ship of Theseus. It has undergone numerous refittings, and not a single part of the vessel as it originally was is present on the current vehicle. This makes researching it quite difficult, as much of the published material refers to older versions of the vessel. I've had to make quite a number of revisions to this script, as I've discovered a system I've researched is no longer present on the vessel. Here we'll focus on the present iteration of Alvin, but I will make reference to historical incidents and configurations where appropriate. I'd also like to make clear that several similar craft exist worldwide, and all have similarly excellent safety records, a testament to the DSV community as a whole. With such a long and varied history, it's difficult to do justice to Alvin in a single presentation. As tempting as it is to talk about the discoveries made by Alvin, this video will focus on the engineering design choices and procedures that have allowed Alvin to undertake almost 5,000 dives safely. Well, there are a few exceptions, but no one has ever suffered a major injury aboard Alvin. I hope this video goes some way to demonstrating the astonishing amount of work required to properly design in redundancy for operations in such a dangerous environment. To begin with, I'd like to go through the systems that make Alvin a submersible in the first place. The Buoyancy Systems, aka how to get to the seabed and come home again. A common misconception for DSVs is they use the same compressed air ballast systems that conventional submarines use. In a conventional submarine, tanks of compressed air are used to blow down ballast tanks, displacing the water for air and making the craft lighter overall, allowing it to float. This is only possible to a certain depth. From experience, around 3,000 metres or 10,000 feet below surface is the commonly quoted practical maximum, but I think there's quite a range on that. Here's why. Let's take a simplified submarine ballast system. Here's a compressed air tank and here's the ballast tank. Air flows through here to displace seawater and make the craft float. This tank needs to hold compressed air at surface at greater than the hydrostatic pressure at our maximum operating depth. So as our depth increases, the air pressure needed increases, and that means thicker walls on our tank, and that means more mass. Let's plot the weight of an air tank needed to operate our sub at a given depth. Now let's plot the buoyant lift force provided by air expansion from that tank. Ideally it'd be constant, but in reality I think it's closer to this, in part due to the ideal gas law falling apart as pressure increases. Okay, the two always cross over, so there's always a point where the mass of a compressed air tank will always exceed the buoyant lift it can provide. The system as a whole cannot lift itself because the air tank always becomes too heavy. As I said, for steel alloys, I think the practical limit is around 3,000 metres or 10,000 feet. You can try and design some novel system like a lift bag or an expanding balloon or something like that, but however you go about it, if you want to come home, you either need to leave your very expensive air tank on the seabed or find another way. In Alvin's case, to get to the seabed and return again reliably but at sufficient speed, several independent ballast systems are required to work together. I've built myself a mini demo submersible, so as we go through each ballast system, I'll add an analogous one to my model. Hopefully that makes the purpose of each system a little clearer. Let's imagine the craft with no ballast or flotation elements installed. In Alvin's case, from what I gather, it'd probably be negatively buoyant and sink to the seabed. The first step is to add something with a low enough density to bring the overall density of the craft down enough to below that of seawater. A light but extremely strong material capable of resisting the pressure at seabed. I'm talking about syntactic foam. This exploits the strength of a hollow sphere but on a small scale. Syntactic foam consists of tiny hollow glass beads bound together with a polymer matrix. It's added to the craft in sufficient quantity to allow it to float freely back up to the surface. But how do we get down to the seabed now? And for that matter, how do we return? To ensure a quick descent to seabed, drop weights are needed. Alvin starts each dive with 6 steel weights attached. This gives the craft sufficient negative buoyancy, when the fixed ballast tank is flooded, to sink to its maximum operating depth in about 3 hours. As it approaches the seabed, 2 of these weights are dropped and the vehicle approaches neutral buoyancy. As the craft is now close to neutrally buoyant, only a small amount of further weight must be dropped to guarantee a return to surface. Dropping 2 of the remaining 4 weights achieves this. These 4 remaining weights are droppable via independent electrical lines. The weight releases can actually be operated from emergency batteries within the cabin. So in the event of a power loss, it's still possible to drop weight and return to surface. It's also worth mentioning that the drop weights are steel and therefore naturally biodegrade with minimal impact on marine life. But now we have the problem we had when we started out. Alvin would just sink immediately when lowered into the water. So we add a relatively large tank full of air to overcome the force of the drop weights. This is the fixed ballast tank that I just mentioned. To submerge, the fixed ballast tank is flooded with water, increasing the overall weight of the craft and sinking it. It's important to note that it's one way due to the limitations of using compressed air, which can't be used at such depths. So when this tank is filled, it can't be emptied until the craft resurfaces. Now we have a craft capable of sinking to the bottom and returning to surface relatively quickly. But we can't just hover over the seabed using solely the thrusters while we're down there. That'd drain the batteries far too quickly. That also just feels off to me. Just more potential complexities in case of a thruster failure. To attain more efficient but limited vertical control while we're down there, we look to the variable ballast system. I believe this is the most mechanically complex of Alvin's ballast systems. As we discussed, Alvin operates too deep for a conventional compressed air system, but a more limited version is possible. The variable ballast system consists of titanium spheres that are filled with air at surface. When submerged, Alvin can pump seawater into these spheres, compressing the air and adding to the overall mass of the vehicle. Likewise, the water can be pumped back out again to add buoyancy. Really, it's just the relatively small compressed air tanks of a traditional submarine variable ballast system tailored to have seawater pumped in and out of them. As this does not rely on air expansion like a typical submarine system, and therefore has relatively small volume, it can only adjust the vehicle buoyancy by a limited amount, and is therefore used to fine-tune the altitude near the seabed. Alvin is trimmed to weigh only about 20 kilos or 35 pounds in seawater with the fixed ballast tank full, and the variable ballast system can alter the weight by up to about 150 kilos or 350 pounds. Not enough to bring the 20-ton vehicle to surface in a sensible time, but enough to allow the pilot to trim Alvin to hover just above the seabed. To provide additional return to surface redundancy, other components can be detached as part of the emergency detach system. The main batteries can be dropped in an emergency. A ballast drop failure isn't the only foreseeable situation where Alvin could be trapped on the seabed, however. Entanglement remains a significant risk, namely in abandoned fishing lines or nets. The most likely part of the craft to become entangled are the thrusters, which are capable of ingesting ropes and jamming. So each thruster can be individually detached via either an electrical or mechanical release. In addition, the manipulators and science basket, which also pose an entanglement hazard, can be detached if needed. Previous versions of Alvin allowed detachment of the entire pressure sphere as a last resort. This capability is not present on the current version, however, as it's been superseded by the independent component detach systems. However, the craft does have an emergency rescue buoy that can be deployed and could allow surface vessels to assist in a rescue. This wouldn't be able to be used to recover Alvin directly. There's no way a buoy could carry up a cable heavy enough to hold a 20-ton craft, but it could feasibly be used to guide an ROV down to assist in an entanglement scenario. Let's discuss one element that can't have a backup, the pressure hull. So how is this designed and built to minimise the chance of failure? As is the case with every other DSV currently in operation, Alvin's crew are housed in a spherical pressure vessel. For Alvin, the hull consists of a titanium alloy. It's quite difficult to communicate the amount of work that went into designing and manufacturing this vessel, so I'd like to walk through an incredibly oversimplified example, and then discuss how engineers at the Southwest Research Institute did it for Alvin. And don't worry, even though the graph paper's coming out, I won't actually do all the maths on screen. We'll just cover the broad concepts. I did a lot of work in the past calculating collapse pressures for tubing in oil wells. That is generally done by doing the most engineer thing possible, pulling out a little green book of lookup tables, finding the required size, and derating the living daylights out of it. For a pressure hull, it's a lot more complicated. To demonstrate, let's do a really quick example for a sphere. No windows, no hatches, no discontinuities. Just a small demonstration sphere that I want to find the compressive pressure failure for. My sphere is constructed of ABS plastic, is 40mm in diameter, and has a wall thickness of 0.4mm. It's a ping pong ball. Let's try and predict the failure pressure for a ping pong ball. Oh, and a quick word on units. I'm really sorry to all my American viewers. You do make up about half my audience. I'm going to have to do all my calculations in metric, but I'll give the answers in imperial too. With that in mind, 40mm is 1.57 inches. In the last video, I showed this graph, where as long as we limit the stress to our material, the strain will be proportional and the material will not fail. That graph's for steel, but we're aiming to stay in this elastic region for ABS plastic in our case as well. For a shell to fail in compression, we just apply enough pressure so the stress exceeds this yield point, right? In fact, it's really easy to calculate the stress in a spherical shell. There's a visual proof of the formula for anyone wanting to try it at home here. We could rearrange this to calculate the thickness of our sphere. Okay? Done? Nah, not even close. It's rare for structures to fail in pure compression. They buckle first. So how do we calculate buckling in a sphere? It's time to pull out one of the classics. And again, don't worry, I'm not going to actually do all the maths. So we start with the previous formula, and imagine the forces acting over a tiny part of the shell whilst moving it ever so slightly. And then we fight our way through all these pages and pages here, and finally convince ourselves that everything simplifies to this formula right here. So, does this result reflect reality? No, because we've just put a spherical cow in a vacuum. Well, quite the opposite of a vacuum, actually. Anyway, buckling is complex and can occur in many different modes. Here are some images of different types of buckling, which can be triggered by small variations in the material or the applied pressure. The formula is simply not intricate enough to capture all these variations. And anyway, after all the work we took to derive that formula, we turn the page and Timoshenko tells us, experiments show buckling occurs at much smaller pressures, and gives us an empirical formula instead that doesn't even apply to a full sphere anyway. So here's a kind of pseudo result for that formula. I've assumed the max buckling size permitted by that formula. Okay, so we have one derived result and one empirical result, which is wildly different. Welcome to non-linear analysis. Are either of these any good? We need another approach, an independent approach to cross-check. We need to simulate the object and the load applied to it. To simulate, imagine taking our ball and splitting it into a number of points. We could apply our force to each point, and since we know its material properties, we could calculate the stress on that point, and therefore how it would move and affect the points around it. We repeat as the points interact with each other, and get a final state where we can see the position of each point. Now, more formally, those points are called elements, and this is called finite element analysis, or FEA. This is something I tended to verify rather than actually do myself, so I might be a little bit rusty here. Let's take our shell, which is displayed here, and apply an external pressure to it. Okay, then we run the simulation and see how it holds up. Okay, not bad. We can cycle through a few different buckling modes and see the safety factor for 3 different types of buckling using this simulation, with the minimum giving it a buckling pressure of 1.2 bar. So what we have now is a prediction from our buckling equation and one result for one load case with one failure mode and 0 derating for defects, manufacturing tolerances, material inconsistencies, etc., etc. It's still nowhere near reality, but it's a good first pass. In fact, at 1.2 bar, the predicted collapse pressure here is actually pretty close to the result from the empirical formula, which was 1.73 bar. Now let's see how it holds up in reality. So at this point, we'd do a physical pressure test. Unsurprisingly, I don't have access to a pressure chamber. So I cobbled together this frankly ridiculous and actually quite dangerous arrangement using a bike pump, a water bottle, and lots of hot glue. I managed to get it up to about 2 bar before it stopped holding the pressure. Well, that's already above the buckling pressure predicted by our simulation and our empirical formula, and the ping pong ball looks fine. Honestly, it's not a huge surprise. 1.2 bar does seem really quite low, but it demonstrates that the assumptions both the models are based on clearly do not reflect the real world. To improve the analysis, we'd have to use different formula with different assumptions, and probably make extensive alterations to our FEA model, or use more customised software. For anyone interested, I did take the ping pong ball and put it in a fence sprayer that's capable of getting up to around 4 bar. On inspection, we see a region that clearly buckled and subsequently elastically rebounded. Anyone who knows the actual collapse pressure of a typical ping pong ball, feel free to let me know in the comments. But for these ones, it seems to be between 2 and 4 bar. I think we get the point now that designing the pressure sphere for Alvin was much, much more complicated than the toy example I just presented. I started by pulling up the physical characteristics of my material from somewhere on the internet. The titanium alloy chosen for Alvin's hull was 6A1-4V-ELI. The ELI there stands for extra low interstitial, signifying a higher purity range than normal. The alloy was actually specifically tailored for the application, with the extra purity providing additional resistance to creep. Creep is yet another potential route to failure caused by slow deformation due to prolonged exposure to pressure. Because this alloy was a specialty composition, its response to compressive stress was not very well understood at the time, so engineers just couldn't look up the material properties like I just did, and they couldn't pull out a little green book with them in either. They had to determine them themselves. So before any manufacture could even begin, samples of the alloy went through physical testing to determine all the required properties for subsequent calculations. Alvin's sphere is rated for 6,500 metres in seawater with a 25% margin of safety. And to be absolutely clear, that margin is after derating for manufacturing, material and other uncertainty defects. Unlike my simple approach previously discussed, there was actually no established methodology for predicting the buckling load for a sphere of the required size and materials. Formulae had been developed for another DSV though, the Seacliff. These were used in the first case with appropriate safety factors. To partially validate these results, custom FEA software was created to simulate the loading and predict buckling failure. The results from the FEA agreed with those of the formulae, allowing the process to proceed to the manufacturing stage. And I'm going to have to put in another quick word on units here. All the material regarding Alvin's sphere construction is a mess between imperial and metric, so I'm just going to have to quote both of them here. I'll generally start with imperial because that's what's quoted, but I'll try and do both. As with so many other aspects of Alvin's design, I cannot do justice to the manufacturing process of the sphere in such a short amount of time. The entire process took 4 years from start to finish, and began in Milwaukee with 2 titanium ingots, each weighing 17,000 pounds, or about 7,700 kilos. These were repeatedly heated and formed into 130-inch or 3.3 metre diameter plates using a rotating paddle. An interesting point of note for titanium, although we typically think of it as a relatively tough material, when heated to the required temperature it actually becomes surprisingly malleable, far more so than steel. This makes forging easier than you may expect. The plates were formed into hemispheres in a hydraulic press with a custom mould. The hemispheres were then shipped to Los Angeles for heat treatment. This involved heating them to an annealing temperature and quenching in water. The annealing and quenching process, in short, both relieves internal stress in the material while increasing its toughness. The next step saw the hemispheres transported to Anaheim for machining. This saw them machined to the required thickness of 2.81 inches or 7.14 centimetres. While titanium's quite easy to forge, machining it is an entirely different story. It's probably why many engineers I used to work with would do anything to avoid using it in our designs. When initially researching this video, my biggest question was, how were the 2 hemispheres joined together to make the final hull? The answer is obvious in retrospect. Electron beam welding. Whenever you see anything with electron beam welding in the description, you know it was expensive. The process involves mating the 2 parts to be welded in a vacuum, and using an electron beam to heat the 2 sides, forming a high-quality weld if done properly. No filler material is used, the 2 sides are fused directly together. I've heard anecdotal stories of electron beam welded tubing being pressure tested, and actually failing in the unwelded zone, not on the seam. I'm not sure how true those stories actually are though. At this point, the inserts for Alvin's windows were also welded onto the sphere. The windows. We haven't even talked about the windows yet. Alvin has 5 acrylic windows mounted in the shape of a wedge, allowing them to be securely seated by external pressure. The thickness was determined from a series of empirical formulae, developed by the American Society of Mechanical Engineers from decades of experience and testing. Before the windows were installed, some additional heat treatment was also performed, basically more annealing to relieve the internal stresses created by the welding process. One of the major sensitivities in the buckling analysis is the deviation from a perfect sphere. A relatively small deviation causes a surprising reduction in the pressure required to buckle shells, and this is particularly of concern for spherical bodies. The maximum permittable deviation for Alvin's hull was 0.125 inches, but when measured, the hull was found to have a maximum deviation of just 0.035 inches over a diameter of 83 inches. That's 0.8 millimetres over 2.1 metres, and that was across the welded section. A remarkable achievement. Finally, the sphere was shipped to Annapolis for a pressure test. 80 strain gauges were installed to the vessel, and using a test chamber that I honestly was surprised even existed, an external pressure of 12,000 psi was applied. This is the pressure found at 8,000 metres depth under seawater. The strain deviation measured on the gauges were found to be in agreement with the expected deviations from the finite element analysis. This concluded manufacture of the sphere, and it was shipped to Woods Hole to be installed into Alvin. Alvin's position in space is known throughout the entire dive. Of course, there is no GPS or radar underwater, so how is this achieved? There are 3 independent systems to achieve this on Alvin, and under normal operation, all 3 complement each other to give highly reliable positional data. Let's walk through them one by one. Imagine plotting the velocity of Alvin over time. To keep things simple, let's just plot the horizontal speed, or the speed in the x direction. Now let's create a second graph, sharing the horizontal, or time, axis. On this graph, I'm going to plot the area under the first graph as we travel along the time axis. This second graph represents Alvin's horizontal displacement, or position. So by summing the area under the speed graph, we can determine Alvin's position at any point in time, providing we know the velocity. The first positional system does exactly this. It's the Doppler velocity system. It operates by sending out sound pulses and measuring the Doppler shift of the return frequency. Pulses are sent out in 3 spatial axes, so velocity can be directly measured in all 3 directions. The system is most accurate near the seabed where the signal can be effectively reflected, but also operates during descent, measuring the partial return from the surrounding seawater. The velocities are continuously summed to provide a position in space. In short, by knowing where we were and how fast we moved, we know where we are now. The problem with summing velocity to obtain position is that of drift. A small error in the velocity measurement accumulates to an incremental error in position. Broadly speaking, it may be thought of as accurate but not precise. So the inferred position must be periodically disciplined with an independent high accuracy measurement. This is the second system, the ultra-short baseline system. The support vessel is fitted with a transceiver which sends out acoustic pulses. Alvin is fitted with an acoustic transponder, or beacon if you will. By sending acoustic pulses from the vessel and recording the bearing and return time of the response from Alvin, its position can be calculated to a reasonable level of precision. Of course, this is insufficient for an accurate position fix, since the acoustic return time is affected by variations in water temperature and density, but it serves to reset the drift in the Doppler-derived position. In short, if we made an error measuring how fast we got here, we can correct for it every now and then. The third system is used for orientation rather than position. It's a fibre optic gyroscope. This is a device I'm not particularly familiar with. I think I did come across one once, but it was literally the week before I left the oil and gas industry, so I don't think I was really paying much attention. I'll leave a source that explains how these work, but for the purpose of this presentation, it's a more precise version of the solid-state gyroscope you'd find in your phone. It's especially good at detecting changes in rotation. As far as I can tell, the precise orientation measurements from the gyro actually assist with the other 2 systems to more accurately determine overall position. A point that I find particularly fascinating, and one that I wasn't aware of prior to this research, the primary underwater telephone can be used as an independent means of determining Alvin's position in space, to some extent. After all, what is an underwater telephone but another form of sonar? The support ship, the Atlantis, has an identical phone. By sending a pulse to the support ship and measuring the response time from the ship's underwater transducer, distance to the support ship can be determined. The same works in reverse. The ship can send a pulse from its phone and measure the response time from Alvin's transducer. In addition, Alvin can independently determine its depth and altitude relative to the seabed by sending a pulse from the telephone and measuring the echo time from surface on its upward-facing transducer, or the seabed on its downward-facing transducer. Position in the Z direction, also known as depth, is the one direction the pilot really doesn't want to get wrong. Alvin is exceedingly unlikely to ever somehow accidentally exceed its max rated depth of 6,500 metres. For one, there are simply very few places that deep. 99% of the world's oceans are within its design depth. Regardless, depth readouts are provided via 2 independent depth transducers. These provide readouts to the digital display, along with an independent gauge which doesn't use temperature correction to calculate depth and pressure, and is therefore more conservative. And of course there's a magnetic compass mounted in front of the controls, just in case everything else fails. Knowing where the craft is great, but the crew obviously need to know what's around them to minimise the risk of a collision. Alvin's therefore fitted with a side-scan sonar unit to detect obstructions. And finally, the crew need to actually see where they're going when they're closer in. There are 12 LED lighting arrays positioned around the vehicle. Each is run on an independent power bus. I believe 2 of these can also switch to green light, which provides better clarity underwater. Within the crew compartment is breathing gas for a minimum of 3 days for 3 crew, well in excess of the typical dive time of less than 12 hours. This includes 2 redundant calcium hydroxide gas scrubbers for CO2 removal. A second, entirely independent breathing system is also available in the form of rebreathers. These are fitted with full face masks and independent oxygen bottles and scrubber material. The purpose of these is to be used in a situation where toxic material is present in the vessel atmosphere, for example, the aftermath of an electrical fire. And in the case one of these emergency rebreathers fails, there is a spare, giving 4 in total. The reliance on a rebreather system does open up a path to a particularly unattractive failure, however. The oxygen bottles must be necessarily stored in the pressure hull with the crew. In the event of an oxygen leak, the crew space would become an oxygen-rich environment and run the risk of a full Apollo 1 situation. Air monitoring sensors continuously provide data on oxygen levels and alert the pilot if safe O2 limits are exceeded. This is also one of the reasons all electronic equipment taken on board must be cleared prior to boarding as part of the safety procedures. I don't know what the protocol in the case of an uncontrolled oxygen leak is, but I imagine it's something along the lines of drop the weights, establish positive buoyancy, and pull the main breaker to shut off all electricals. As with any crewed vessel, a quick look around reveals a couple of fire extinguishers. A final life support consideration was added in the 1980s. It was realised the life support would probably outlast the crew on the seabed due to hypothermia, so vacuum-packed sleeping bags are also available. Constant communication between Alvin and the support ship is essential, from a safety point of view, but also for communicating scientific data. Therefore, at least double redundancy is present for Alvin's communication system. These systems are some that I'm less familiar with from experience, so I won't speak at length about comms. The primary means is via an UQC underwater telephone. This is a system familiar to anyone involved in crewed subsea operations and is present on every US Navy subsea vessel. It's colloquially known as Gertrude. The principle of operation is deceptively simple. Although light does not travel well through water, anyone who's put their head underwater in the swimming pool will know sound does propagate well. So, underwater telephones are really just a glorified speaker and microphone, which we'll refer to as transducers from this point. To send outgoing voice communications, the voice signal is shifted to a higher frequency, as higher frequencies propagate better in water. It's then broadcast through the water and received by the complementary transducer on the support vessel. There, the frequency is shifted back down to audible levels. There is some signal processing involved to aid in effective data transfer, but the basic principle remains that, pretty basic. To provide redundancy, Alvin has a second subphone underwater telephone, which is also available to broadcast and receive voice data as well as text communications. In addition, the USBL, ultra-short baseline system present on Alvin, which is normally used for communicating science and position data to the vessel, may also be used for text-based communication. For surface communication, a standard marine VHF radio is in place. Until just a few years ago, Alvin's primary power supply was 2 banks of lead-acid batteries. This certainly sounds surprising at first. Lead-acid is one of the oldest and least energy-dense battery chemistries available, though, ignoring their widespread use in cars, they still use a surprising amount in industrial applications. My previous employer had a bank of them as part of their uninterruptible power supply to their compute cluster. This was due to their reliability and ability to deliver an impressive current in an impressively short amount of time. Nevertheless, in recent years, Alvin was fitted with modern lithium-ion battery banks. This was necessary to certify the vessel to reach 6,500 metres, as the extended ascent and descent times required additional battery capacity. To mitigate against the potential fire hazard caused by this new chemistry, extensive tests were required to identify potential failure modes and minimise their chance of occurrence. And drawing power from these batteries are the 7 thrusters. They're controlled via a pair of joysticks in front of the pilot's seat. A redundant control system is available via potentiometers, which can be used to preset a given motion. To reduce task loading on the pilot, and therefore reduce the chance of an operator error, a suite of automation options are available via the digital displays. These include automatic hover hold and automatic depth and XY position locking. In other words, the position of Alvin can be fixed on any axis or combination of axes thereof, allowing the pilot to avoid making constant adjustments. A second system provides pitch trim, and this is a physical system, the mercury ballast system. This consists of tanks of mercury positioned around the vehicle and connected by high-pressure pumps. By pumping the relatively heavy mercury from one location to another, Alvin can be trimmed to hold a given orientation without the need for constant thruster input. This is especially useful when tracking along a sloped seabed, allowing the pilot essentially to point forward and go. Although Alvin has never caused serious harm to its crew, his past is not without incident. A couple of years ago, during Alvin's progressively deeper dives to get the final certification for 6,500 metres depth, cracking was discovered on the newly installed syntactic foam. The failure was determined to be due to the interface between the foam and the frame, with differential strain between the materials as the craft descends. It sounds like the problem was taken extremely seriously, with the lead engineer actually flying back to Woods Hole from the dive site to start work on remediation as soon as possible. The problem was resolved, and Alvin was subsequently cleared for dives to 6,500 metres. We could play out a scenario where the syntactic foam became detached and Alvin was trapped negatively buoyant on the seabed. I would be astonished if this was a remotely viable scenario, but devising and subsequently ruling out such failure scenarios is one of the major aspects of designing safety into any crewed system. Alvin had a far more serious incident in 1968, with a lift cable breaking and it falling into the sea with the hatch open. Luckily, the crew were able to escape, and the vessel spent several months on the seabed before, somewhat incredibly, being recovered. Being so far in the past, this is not an incident I'm going to discuss at large, but the findings from it were used to improve procedures going forward, and nothing even approaching that level of severity has occurred on Alvin since. The book Water Baby recounts some other incidents in Alvin's pre-1990s past. They include collisions with underwater cliffs, electrical failures, and forgetting to turn on the CO2 scrubbers. My favourite is an account of a 1974 dive where a passenger smelled burning, leading to the pilot, and this is a direct quote, opening this little electrical box and cutting every wire. Then he went back and found which wire it was, left that unconnected, and reconnected the others. Though somewhat comical, a nice reminder that Alvin's natural environment is far from risk-free. We could even say Alvin has redundancy in its certification process. The craft has two completely independent certifications, possibly owing in part due to the joint interests of its military owners but civilian operators. The first certification is from NAVSEA, or Naval Sea Systems Command, a branch of the US Navy. The process of gaining certification from this body is particularly famous, as it is often used as a case study in proposals for engineering projects. Part of NAVSEA certification involves adhering to the SubSafe program, which assures quality standards in manufacturing and building submersible vehicles. SubSafe was born from the loss of the USS Thresher, an incident that's discussed at length in other videos on YouTube. Alvin was actually the first DSV certified under SubSafe. As much as I'd like to walk you through the stringent requirements for NAVSEA certification, the often quoted fact is that since SubSafe was established, the US Navy has lost only one submarine to non-combat incidents. And that submarine did not have SubSafe certification. The second body to certify Alvin is the American Bureau of Shipping, or ABS, not to be confused with the ABS plastic my ping pong ball is made of. During the design of Alvin's pressure hull, it was realised a hull with sufficient thickness to meet ABS standards would not be viable on Alvin due to weight constraints. By developing the new calculation techniques I discussed earlier, in conjunction with the Navy certification, the engineers at the Southwest Research Institute were able to work with ABS staff to eventually redefine some of their pressure hull standards to allow for the new design, as the additional verification process proved sufficient to ensure an acceptable degree of safety. This flies against the mantra of certification being a barrier to innovation. By working with the ABS, Alvin's designers were able to improve and update the standards for everyone, therefore opening the door to new design methods going forward. As I continue to stress, certification often feels like an extremely expensive tick box exercise. But when you're under 4 miles of seawater, it's good to have someone else go over your calculations. With its latest round of upgrades recently completed, Alvin is once again making regular dives, and will no doubt continue to further our knowledge of the deep oceans for decades to come. I really hope this presentation has been an effective demonstration of the fact that, although some environments are inherently hostile to human life, with the appropriate amount of planning, precaution, verification, and ingenuity, it's possible to send a crew almost anywhere. It's never cheap, but that's the cost of exploration, and exploration is what makes us human. Thank you so much for watching.